Alright, so this tutorial is on how to control the ADC0831 manually and also with the Parallax Propeller microcontroller using the simple IDE platform for C and C++. This ADC is one channel 8-bit analog to digital converter which uses the SPI synchronous serial communication protocol. Here's the schematics for this exercise from the Parallax Basic Analog Digital book. Alright, so for the purpose of manually communicating with it, the chip select pin is now connected to DAP switch 0 here, and also the lower LED on the LED strip. The clock is connected to the microcontroller's pin number 3, and the middle LED on the LED strip, and the DO pin or data output from the ADC to the top LED. The purpose of the LEDs here is so we can tell whether a pin is high when on or low when off. Instead of a push button being used here directly into the clock, we'll be using this function, which waits until the push button is pushed and sends a 1 second clock pulse represented here in microseconds. In case you're wondering why the push button isn't connected directly into the ADC chip in this example, it's because one push with this kind of a push button is often represented as more than one clock pulse by these ADC chips because they work fast in the microsecond scale. So for the clock pulse, we will use the microcontroller, but still trigger manually. Like that. Alright, so this timing diagram is a sequence of steps needed for acquiring the data. This ADC chip works in MSBPOST mode. Post means that the data should be read on the falling edge of the clock. In other words, after the clock goes low, as in here, or it would look like there. Alright, so an MSB means bits are going to be sent out one by one from largest to smallest, as in here. Okay, so from the beginning, the chip select pin is high, which means inactive, and the clock is low. On the next step, the chip select pin needs to go low in order to enable the ADC. This also selects this chip if we had more than one sharing clock and data lines. So now the ADC is ready to take a measurement as soon as the clock pulses once, like in the diagram sequence here. So we turn the chip select low to enable and set a variable resistor to any random value and send the clock pulse. Now the ADC has a volts measurement stored in its memory register, which we're going to retrieve as a binary number. Notice that the data pin is low. This is a null bit. Now let's send the next clock pulse in order to get the first bit of our number. Our data LED is off, which means 0, so we mark it as a 0. Let's do the next one. Alright, so our data LED now is 1, so we mark it as a 1, and we keep doing the other 6. And after that, you can just keep clocking and nothing is going to happen until you reset. So now that we have the measurement represented as a binary number, let's turn it into a decimal number by multiplying each column and then adding them up. Alright, so 0 times 128 is 0. 1 times 64, 1 times 32 equals 32, 0 times 16 is 0, 1 times 8, 1 times 4 equals 4, 0 times 2 is 0, 0 times 1 is 0, 4, 5, 6, 14, 18, 6, 7, 8, 9, 10. And that's our decimal number. So that was a decimal representation of our binary number, which we now, if we want to convert to volts, first we measure this board's 5-volt regulator, because it's the one the ADC is using as a reference. So let's see, 5 volts, 5.06. This ADC is capable of 256 binary values, but since the first value is 0, there are 255 voltage steps. So let's divide the result by 255. Let's take that and multiply it times the decimal number we just got. And that's our volts measurement. Well, let's see here. If we connect it back in here, there it is. Alright, so let's do another one real quick. Adjust to whatever. Alright, random. And alright, so here's the code. First, pin 0 through 2 are declared to their constant. Then we follow the timing diagram's flow with a high chip select followed by a low clock. After that, it gets into an infinite loop in which first a low chip select command enables the ADC, followed by a 210 microseconds clock pulse. And then the shifting commands take care of the sending clock pulses and reading the data line. Now, because the first clock pulse returns a 0, also known as a null bit, the pulse out can be removed and the extra clock pulse needed can be added into the shift-in function in order to keep it simpler and potentially faster. Alright, so if you like this video, stick around and I'll see you.